Physiology notes of all my theory videos is available now. To get your copy, you can WhatsApp on 72650 This book attempts to come up with important questions and appropriate answers in easy way. In this book, different systems are discussed under 10 sessions, and each section is framed with different topics in the form of question and answers. It provides thorough coverage of subject and made it easy to write down answers in the exams. Hello everyone, today we will discuss about mineralocorticoids. Chief mineralocorticoid or most potent mineralocorticoid, that is aldosterone, which has 90% mineralocorticoid activity. You can see the structure of aldosterone. Another is deoxycorticosterone, that is 1/30th time potent as compared to aldosterone, and it is secreted in small amount. 18-hydroxydeoxycorticosterone, that is also secreted in small amount. Aldosterone's mineralocorticoid activity, that is 3000 times greater than cortisol, but plasma concentration of cortisol is greater than aldosterone. Now, aldosterone is transported in two forms. You can see here, one is bound form, that is about 60%, and it is bounded with globulin and albumin. The globulin is known as aldosterone binding globulin, or which is also known as transcortin, and the albumin. Second, that is free form, which is 40%, and half-life of aldosterone, that is 20 minutes. Steps for the synthesis of aldosterone, you can see here. This cholesterol that is converted into pregnenolone by the enzyme cholesterol desmolase, which is also known as P450 side chain cleavage. This pregnenolone is converted into progesterone by the enzyme 3-hydroxy steroid dehydrogenase, and this progesterone is converted into 11-deoxycorticosterone by the enzyme 21-beta hydroxylase. 11-deoxycorticosterone is further converted into corticosterone by 11-beta hydroxylase, and corticosterone is converted into aldosterone by aldosterone synthetase. Here you can see these are the steps again. Some of the steps they are in the mitochondria, and some other steps they are in smooth endoplasmic reticulum. You can see here, first one that is carried out in the mitochondria, second and third in the smooth endoplasmic reticulum, and remaining are in the mitochondria. Now, plasma level of aldosterone, that depends on the sodium intake. When sodium intake increases, aldosterone secretion decreases. Aldosterone secretion, that is 50 to 250 micrograms per day. Second regulator, that is diurnal variation. You can see here the concentration is highest in the morning. You can see here in this diagram, this one, it is highest in the morning and least in the evening. And this diurnal variation of aldosterone, that is not affected by change in the sodium potassium level as well as change in the posture. Next is zona glomerulosa. You can see here, this is the part that secretes aldosterone. The zona glomerulosa is minimally influenced by ACTH. And therefore, aldosterone secretion is regulated not by ACTH but by renin-angiotensin system. Second, that is plasma potassium level, and third, that is atrial natriuretic peptide. Next is metabolism of aldosterone. In the liver, 90% of aldosterone, that is conjugated with glucuronic acid. You can see here in the liver, and it forms tetrahydroglucuronide conjugate, this one. Small amount of aldosterone, that is conjugated in the kidney, and it forms aldosterone 3-glucuronide conjugate, and very small amount that is also converted into aldosterone 18-glucuronide conjugated. This one, aldosterone 18-glucuronide conjugate, that is also known as acid labile conjugate. This is acid labile conjugate, and it is measured for diagnostic purpose. Why is it known as acid labile conjugate? Because at acidic pH 1, this aldosterone 18-glucuronide conjugate, that is hydrolyzed, and it forms free aldosterone. Now, excretion of different forms of aldosterone. 40% of aldosterone, that is excreted in this form, tetrahydroglucuronide conjugate. 5% in this acid labile form, this one, 18-glucuronide conjugate, and only 1% that is in free form. Now, mechanism of action. As we all know that aldosterone is a steroid hormone. So you can see here in this diagram, because having lipid solubility, it can easily pass through the cell membrane. It can enter inside the cell receptors are present in the cytoplasm. So mineralocorticoid receptor, it binds with the receptor, and when it binds with the receptor, this hormone receptor complex, it enters inside the nucleus and it causes this transcription and messenger RNA synthesis. Okay? Now this messenger RNA which is produced, that diffuses in the cytoplasm and that results in the protein synthesis. These proteins are either enzymes or membrane transport protein. This membrane transport protein, they are important for the transport of sodium and potassium ions. This is mainly aldosterone induced protein AIP, which is responsible for the sodium transport, and there are three hypotheses for the transport of sodium by aldosterone induced protein. They are, let us discuss. One, that is sodium potassium pump hypothesis. Here aldosterone induced protein, it acts and it increases the activity of sodium potassium pump. That is one hypothesis. Second, that is metabolic hypothesis. You can see here this aldosterone induced protein, that increases the metabolism, and as the metabolism increases, what happens? Because of oxidative metabolism, ATP synthesis increases, and this ATPs, they are important for sodium potassium pump to get active. So that is second, is metabolic hypothesis. And third, that is permease hypothesis. Means aldosterone induced protein increases the permeability of the membrane. Permeability of the membrane to sodium from tubular lumen, and that is by this epithelial sodium channels. Okay? This epithelial sodium channels, they get activated and there is passive transport, or you can say transport along the gradient. Okay? So these are three hypotheses. One is sodium potassium pump hypothesis, second that is metabolic hypothesis, and third that is permease hypothesis. Now, this cortisol, as we have discussed, cortisol is also having mineralocorticoid activity. Cortisol bind to the mineralocorticoid receptors and it has very high affinity. But this cortisol in the renal epithelial cells, you can see here, there is one enzyme 11 beta hydroxysteroid dehydrogenase type 2, which converts this cortisol in inactive form, that is cortisone. This cortisone cannot bind with the mineralocorticoid receptor, so that mineralocorticoid activity is not being carried out. But suppose when there is deficiency, genetic deficiency, you can see here it is shown that there is deficiency of this enzyme 11 beta hydroxysteroid dehydrogenase type 2. So what happens is cortisol is not converted into cortisone, and therefore cortisol is present in the active form, and that is responsible for its mineralocorticoid like activity, and there is a syndrome which is known as apparent mineralocorticoid activity or apparent mineralocorticoid excess syndrome. Here you can see mineralocorticoid activity is in excess, but aldosterone level is low. Now we'll discuss actions of aldosterone. Aldosterone has target organ, they are kidneys, sweat glands, salivary glands and colon. Main function of aldosterone, that is to maintain sodium and potassium concentration, and by maintaining sodium concentration it also maintains blood volume and extracellular fluid volume. Now how it works? It has action on the renal tubules, mainly it has action on the principal cells of collecting duct, as well as small amount has its action on the distal tubule. Now, how it works? It increases the reabsorption of sodium ions and increases secretion of potassium ions from the renal tubular cells. So, it results in conservation of sodium and excretion of potassium ion. Another action, that is through sodium channel, epithelial sodium channel, and that is responsible for you can say that passive transport of sodium ions. Potassium excretion, here very important thing, it depends on sodium, provided by potassium excretion depends on the sodium, and it is proven when there is lack of sodium or sodium deficient diet is there, then now effects on sweat gland, salivary glands. Primary secretion, you can see here in the sweat gland or salivary gland, it is rich in sodium and chloride ions, and when this secretion passes through duct, what happens is sodium ions and chloride ions are reabsorbed and potassium and H+ ions are secreted. This reabsorption is increased by aldosterone. So thus you can see here aldosterone increases reabsorption of sodium and chloride ions and increases secretion of potassium and H+ ions. So it conserves sodium and it increases excretion of potassium ions. Now effects on colon. Here also aldosterone stimulates reabsorption of sodium ions and excretion of potassium ions. Now, when there is excess aldosterone, what happens? As we have discussed, aldosterone increases reabsorption of sodium and increases potassium secretion. So, potassium loss in the urine is increased. As in the urine potassium is lost, as well as it also increases transport of potassium ions inside the cell. So, what happens? Potassium is excreted in the urine as well as transported inside the cell. So what happens? There is decrease in the plasma potassium ion concentration, and when the plasma potassium ion concentration falls below half the normal value, that is 4.5 milliequivalents per liter, when it becomes about 2 milliequilibrium per liter, that results in severe muscle weakness. Now, what happens when adrenal cortex is removed? As we have discussed, aldosterone increases reabsorption of sodium ions. So here reabsorption is lost. So what happens? There is loss of sodium ions. 10 to 20 gram of sodium is lost, which is 1/10 or 1/5 of the total sodium in the body. Now what happens? Sodium and water loss. Sodium loss is more than water, and because of loss of sodium and water, what happens? There is decrease in the extracellular fluid, and because of that there is hypotension, and if water intake is not sufficient, that results in dehydration. There is circulatory collapse and death. Along with that, there is hyperkalemia. Other symptoms are same: dehydration, circulatory collapse and death. So you can say that aldosterone is essential for life, which is known as life-saving adrenocortical hormone. Now, when aldosterone, that is in excess amount, as we have discussed, there is reabsorption of sodium as well as water and increase in the extracellular fluid volume, so increase in the arterial pressure. Here sodium concentration will not be affected more, because when sodium level increases, along with that water is reabsorbed. There is osmosis of water, and therefore you can say that blood volume increases. Here, therefore you can say that whenever there is excess aldosterone, what happens? Sodium potassium ratio in the plasma increases. Why? Because hypernatremia and hypokalemia. So the ratio, which is normally 30, now it is raised. And what happens to the ratio in the urine? Because in the urine you can see that sodium excretion decreases and potassium excretion increases, so the ratio decreases. Now, another effect is aldosterone escape. Now what is escape? Escape means escape from the action, means aldosterone is available but the action is not visible. Now what is it? Let us explain. So here you can see, when aldosterone level increases for a long period of time, or for per se 1 to 2 days, because of increase in the aldosterone level, there is sodium reabsorption that results in increase in the extracellular fluid volume, increase in the blood pressure, and because of increase in the blood pressure, there is pressure diuresis and pressure natriuresis. Sodium and water loss increases, and therefore the effect of aldosterone, which is reabsorption of sodium, reabsorption of water, that is absent, and that is known as aldosterone escape. Now, here what is the mechanism, probable mechanism? Here you can see in this diagram, aldosterone increases, sodium ions, they are retained in the body initially. Along with that, there is osmosis of water, and that results in increase in the extracellular fluid volume, increase in the blood pressure, and the probable mechanism here is atrial natriuretic peptide, that secretion increase in the atrial natriuretic peptide, and that causes loss of sodium in urine. So this is the mechanism. Now, this escape phenomena is sometimes not found mostly in edematous patients, or in cases of congestive cardiac failure, or there is nephrosis or liver cirrhosis, or sometimes toxemia of pregnancy. Why is it so? Because renal blood flow is reduced in all those conditions, and decreased sodium supply or decreased sodium entry at the distal convoluted tubule. So the effect of atrial natriuretic peptide is not seen. Now, effects on the sweat glands, salivary glands, and intestinal epithelial cells we have already discussed. Effect of aldosterone is reabsorption of sodium and secretion of potassium ions. Okay. Now, what are the effects on the water excretion as well as regulation of extracellular fluid? Aldosterone has no direct effect on glomerular filtration rate, renal plasma flow, and renin production. But how does it affects? You can see here, this is renin-angiotensin mechanism. Here aldosterone is secreted here. Okay, and when aldosterone is secreted, what happens? There is reabsorption of sodium, increase extracellular fluid volume, and as the extracellular fluid volume increases, there is increase in the GFR, increase in the renal plasma flow. But when there is increase in the GFR and renal plasma flow, the effect is decrease in the renin production. So these are the effects by aldosterone. Now, what is the role of aldosterone in acid-base regulation? Here you can see, as we have discussed, aldosterone increases reabsorption of sodium and excretion of potassium ion. Along with that, if potassium ions are not there, then there is excretion of hydrogen ions in the distal convoluted tubule. You can see here in this diagram, this is potassium ion is excreted here. In this other diagram, I'll show you. It is more visible here. You can see this. Initially, sodium ions are reabsorbed, potassium ions are secreted. You can see here. But in intercalated cells of collecting duct, you can see here, collecting tubules, you can see there is secretion of H plus ions here. Okay, and what happens when there is secretion of H plus ions? Whenever there is aldosterone in large amount and secretion of H plus ion, that results in metabolic alkalosis because acids are secreted. Okay. Now, what are the secondary effects of aldosterone? Excess aldosterone, as we have discussed, hypernatremia, hypokalemia, retention of water, and that produces increase in the extracellular fluid, and there is hypertension. Okay. And decrease in the potassium concentration produces muscle weakness. Another effect of excess aldosterone secretion, that is, as we have discussed, there is secretion of H plus ions also, and when H plus ions are secreted, that results in metabolic alkalosis. We have already discussed. Now, what happens to urine? Urine becomes acidic because large amount of H plus ions are secreted. Now, another thing is hypokalemia has also other effects. It also affects the secretion of insulin, because for insulin secretion, potassium channels are required and glucose tolerance is reduced because of decreased secretion of insulin. And prolonged hypokalemia also may produce nephropathy, and because of that there is polyuria and polydipsia. Okay? Now, what are the effects due to lack of aldosterone? Lack of aldosterone produces hyponatremia and hyperkalemia, and hyperkalemia produces cardiac toxicity. Also, there is weakness of the heart, contractions are also affected, also produces arrhythmia, and therefore you can say that aldosterone is essential for life. Now, regulation of aldosterone secretion, that is by two mechanisms. Number one, that is extrarenal, and second, that is intrarenal mechanism. Starting with extrarenal mechanism, first and foremost stimulus for the secretion of aldosterone, that is hyperkalemia, means increased potassium ion concentration in the extracellular fluid. That is most potent stimulus, and it is having marked and rapid effect. It acts directly on the zona glomerulosa cell, and it acts by direct stimulation of adrenal cortex. Also, actions are similar to angiotensin II, and it opens calcium channels by depolarizing the membrane. Second stimulus, that is hyponatremia. Hyponatremia affects aldosterone by again two mechanisms, either through renin-angiotensin system or by direct stimulation of adrenal cortex. Third, circadian rhythm of the aldosterone secretion, we have already discussed. It is not affected by sodium, potassium or posture or any other thing. Fourth one, that is angiotensin II concentration in the extracellular fluid, also increases the aldosterone secretion. Another, that is atrial natriuretic peptide, that inhibits renin secretion and decreases the effect of angiotensin II on the adrenal cortex. Next is intrarenal mechanism, that is renin-angiotensin aldosterone system. As we have already discussed, whenever there is decrease in the blood volume or blood pressure or blood sodium concentration, there is increased secretion of renin. Renin secretion increases. Now, this renin, you can see it increases the angiotensin II. Now, how this angiotensin II works? Angiotensin II binds with the receptor. The receptors are G protein coupled receptor, angiotensin 81 receptor. which is present on the zona glomerulosa, and this receptors, they activate phospholipase and they increase protein kinase C, and there is increased conversion of cholesterol to pregnenolone and also increases conversion of corticosterone to aldosterone. So first and last step, they are stimulated and aldosterone secretion increases. Now, there are various conditions they affect aldosterone secretion. They are one that is acute hypovolemia, volume is reduced, like after hemorrhage or if diuretic therapy is given or salt depleted diet is given. Acute hypotension, either may be because of blockage of the ganglion or change in the posture, postural hypotension may be there. Chronic disease with edema, as we have discussed, cirrhosis, congestive cardiac failure, nephrotic syndrome, also decrease blood volume and increase aldosterone secretion, and increase sympathetic activity because of upright posture, exercise, catecholamines, and potassium depletion. Now, what is the role of sympathetic activity on the aldosterone secretion? Here you can see, because JG cells, you can see they are innervated. JG cells as well as afferent arteriole, they are innervated by sympathetic nerve fibers. These are post-ganglionic sympathetic unmyelinated nerve fibers. When this renal nerves are absent, there is renal response to depletion of sodium is reduced. Means if we cut this renal nerves and we reduce sodium level, in spite of decrease in the sodium level, this renin secretion will not be increased. Okay? Now we discuss what happens when this sympathetic nerves are present. So what happens whenever there is decrease in the sodium level? This nerves, they get activated, as well as because of any situation when the sympathetic nerves are activated, what happens? There is vasoconstriction, afferent arterioles are constricted, and that results in decrease in the perfusion, decreased blood flow to the kidney, this glomerulus, and that increases release of renin, and this effect is mediated through beta adrenergic receptors. Okay. Now, what is the role of renin? As we have discussed, renin is secreted in this all conditions: hypovolemia, hypotension, circadian rhythm, chronic disorders, sympathetic activity. They all increase renin secretion and stimulate renin-angiotensin aldosterone system. Renin secretion is reduced when the level of angiotensin 2 and 3 is increased, when there is increased ADH, hypernatremia, hyperkalemia, and prostaglandins, they all decrease renin secretion. So this is all about regulation of aldosterone secretion, and this is all about mineralocorticoids. Thank you.